Welcome to 2809 ICT and 7004 ICT. This is Chapter 3, Network Protocols and Communications, and we're going to go through basically a lot of background information that we're going to find useful as we go through the course. So the topics that we're going to talk about are, first of all, the rules of communication. So again, with these lectures, the way they set out is they have the overview first, so we're just going to go through the topics, and then we'll go through more detail for each of those topics. So the rules of communication, we'll talk about how rules facilitate communication. We'll describe the types of rules that are necessary to successfully communicate. We'll look at some network protocols and standards. There are quite a lot of them. We are going to focus on some for this course, definitely not all of them. We'll talk about the role of a protocol. Actually, we'll also talk about what a protocol is, and some standards organizations in facilitating interoperability in network communications. Explain why these protocols are necessary when we want to communicate. I'll try and relate it a little bit to in-person communication, so the stuff that we do normally as people. It's not quite the same, but there are some similar strategies and rules in play. We'll explain the purpose of adhering to a protocol suite. Can you please not come in through that door next time? It's a bit confusing and disturbing for the people in the class. Thanks. Explain the role of standards organizations in establishing protocols for network interoperability. Explain how the TCP/IP model and the OSI model are used to facilitate standardization in the communication process. We'll talk about data transfer in the network, and we'll explain how devices on a local area network access resources in a small to medium-sized business network. How data encapsulation allows data to be transported across the network. We'll also discuss what is data encapsulation and how local hosts access local resources on a network. So first, we are going to talk about the rules of communication. So there are a bunch of things that we need to be aware of or to consider when we're looking at communication. There's a group of rules. So the first thing is the rule establishment. We need to identify the sender and the receiver, who it's coming from, who it's going to. Now, you've already seen some of those notations in the lab. For example, you would have found that we had an IP address. That's one form of address that we can use to uniquely identify either me as a PC or someone else somewhere else as another PC, for example. We must use some kind of common language in grammar. Okay, and there's some issues around speed and timing of delivery. So just as an example, in this lecture theatre, right, we have agreed somewhere that we will be speaking English. Is it possible for me to change languages halfway through the lecture? I could start speaking French. Would that be useful for you as a student who's expecting an English language session? No, right? So we have some rules and we're going to stick to those. Okay, and we have set those rules up before we started the process. Okay, there's some issues around speed and timing of the delivery. I can speak very fast. I'm not going to speak very fast, but I could. If I speak too fast, what will happen to your understanding? Likely, your understanding will drop, right, because you can't process the words quickly enough to get the understanding. Okay, same thing with a network. If you send too much information across the network, the other side will not be able to, at some point, process all that information. You will lose information. You will drop packets. You will drop pieces of the message that you actually need. We also have some confirmation or acknowledgement requirements. And so if I say something to you, now in person, I'll just look at you and I'll notice that either you understand or you don't understand based on your facial expression, let's say. Right, so in the network that's not possible, so we need to physically acknowledge something. So you'll send me a message and I'll say I got it, right? And if you don't get the message saying I got it, then you can assume after some point of time that that message was not received. Then you can take appropriate steps. You can see how this kind of works. What I'm trying to do, hopefully, is just relate it to something that you're already familiar with, which is human-to-human communication, and you can try and visualize some of the same requirements for a network. Message encoding, the process of converting information into another acceptable form. So we might have to translate things, right? Because not every person speaks the same language, for example, and not every device speaks the same language either. We'd talk about message formatting and encapsulation, the message size, the message timing, so an access method, flow control, response timeout. We'll talk about these in more detail in a minute, by the way. And message delivery options, unicast, multicast, and broadcast. Okay, and so in the middle there you see the protocols, and then around the outside in the green little diagrams you'll see all the different things that we're going to be looking at in terms of the rules of communication. So all communication methods have three elements in common. They have a source or a sender, they have a destination or a receiver, and there's a channel or a media or a medium that we're working through. And rules or protocols govern all the methods of communication. So here's an example. So what I'm going to do, I'm just going to jump into the drawing part here, and I'm just going to draw on this diagram just to make it a little bit more dynamic than just talking about it. So basically human-to-human communication. We've looked at this already. So basically there's a message source, the signal is a transmitter, there's a transmission medium, there's a receiver, and there's a message destination. So we can plug in people here. So the message source will be this person, the message destination will be this person. They are also the transmitter and the receiver, and the transmission medium is, in this case, the air in between them. Okay, so nothing new here, right? We're familiar with this model. Computer communication, there's a message source, there's a transmitter, there's a transmission medium, that's this cable it looks like in this case, there is a receiver, and the message destination. Now, there are actually a lot of steps that happen when we transmit information over a network between two computers. You'll see there are quite a number of layers that we need to implement to do all the different jobs or processes, and they each have their own responsibility, and we'll talk about that when we get through towards the end of the lecture. So protocols are necessary for effective communication, and they include, as we already mentioned, an identified sender and receiver. Who is sending the message, who is receiving the message. I need to know where it's going, and when you get it, and if you're the receiver, you need to know who to send it back to if you want to respond. Okay? There's a common language and grammar, there's some speed and timing of delivery, confirmation or acknowledgement requirements. Let me have a look just quickly. Here's a diagram, and this is from the examples. So have a read of this text. What is your experience with this text? It's hard to understand. Now you can probably work out most of it, right? It's still written in English, at least the first part. But then it changes languages. This does not follow some standard rules that we would expect for a communication. For example, the spelling is not correct, the grammar is not correct, the words are glued together, the language changes halfway through, right? So what we would like is a standard set of rules for the communication. If we start in English, we would appreciate it if you would finish in English. And if you do use English, then you use the English grammar and language rules, whatever they are, right? So the same thing will happen with networking. So that's the common language and grammar part, right? We didn't have it, or not a very good example of it in that diagram I just showed you. So the first part I think we've covered mostly, right? So basically we've got the sender receiver, the common language and grammar, speed and timing of delivery. I mentioned how fast I speak. Can we speak at the same time in a lecture? Probably not, right? If the lecturer is speaking, typically the students don't speak. Now, depending on the lecture and the environment, maybe it is possible, but in general it's not for a lecture environment. What about a workshop environment? Is it different from a lecture? Do you have different rules, right? So you can imagine that there are different categories of messages that we're transmitting depending on the context. And confirmation or acknowledgement requirements. So in a lecture, I mean, I'm just looking around and seeing whether people understand or not just based on your body language, your faces, right? In other environments, I might actually physically check, did you understand this? Right? So I would require an acknowledgement in that case. So the second part that we've got down the bottom here, the protocols and the network communications, they also define a bunch of things, and we'll talk about these in more detail in the next few slides. But there's message encoding, message delivery options, message formatting and encapsulation, message timing, and message size. So there's a whole group of things that we would look at. So message encoding, the first one. encoding between hosts must be in an appropriate format for the medium. That means if we want to send something over a particular type of media, right, or medium, then we need to make sure it's in the right format. Messages are first converted into bits by the sending host. So this is the same diagram we saw before. There's the person or the machine that's sending stuff. To send it across, let's say, a cable, you have to convert it into whatever the cable is capable of transmitting. Typically, it's an electrical signal, high and low, high and low, high and low, right? And high and low would correspond to the binary 1 for on and 0 for off. So as long as you can generate signals as ones and zeros, then the physical medium can translate those into electrical signals. And on the other end, you can receive electrical signals, and if you get a high, you can transfer that into a 1. Low would be a 0. So each bit is encoded into a pattern of sounds, light waves, or electrical impulses, depending on the network media. And again, it's different for different types of media. And then the destination host will receive some of these signals. And if you're following the right rules, it will receive the signals in the right way, and it will be able to make sense of those signals according to what you sent. So the message that you send would be the same as the message that they receive. If you don't follow those rules, then that's not guaranteed to happen. Message formatting and encapsulation. So there is an agreed format, and I'm sure you've all seen it, for things like letters. So if you send a letter to someone, where does the address of the person that you're sending it to go? Like this diagram. In the middle of what? Of the envelope. And which side of the envelope? The front, usually, right? So there are some rules for sending letters, and so on the back you might have the recipient. Now this one has actually explicitly said who is the sender and the recipient. Okay, so they've added some extra information, but typically the recipient is on the front, the sender is on the back, and there's a stamp somewhere on the front usually as well, something that indicates that value has been added to that letter. So putting the letter, if you write a letter, say 10 pages, you write one, putting the letter into the envelope is called encapsulation. Okay, the idea of encapsulation is basically, you're probably familiar with the idea of a capsule, right? Like, so you go to the chemist or a drugstore and you buy some medicine. Usually you get it in tablets or capsules, and inside a capsule is some stuff, and the capsule keeps it safe. Yeah, it contains all the stuff. Same thing with a letter. If you put the separate pages into one single envelope, it's all self-contained, and the envelope travels around the world, for example. It's the same thing that happens to a computer message, but we don't have physical envelopes, right? So it's a bit more abstract. Each computer message is encapsulated in a specific format. It's called a frame, and that happens before it's sent over a network. A frame acts like an envelope, and it provides the destination address and the source address, and potentially some other information as well, depending on what protocols are being carried. So, that's another example. Here is an example of some encapsulation. So you notice the capsule down the bottom, just to give you that idea. When you see the word encapsulation, just think of a capsule that contains stuff. And you might have multiple capsules. Yep, a capsule within a capsule within a capsule. It's possible. You'll see later in this lecture, we'll talk about layers of the network model, and each layer does a little bit of work, and it passes that work to the next layer, which does a bit of work. So if you look in the middle here, that purple thing, so the purple thing here is the encapsulated message. This is the information that we want to send. There is a start flag of some kind, somehow that tells you this is the start of the message. There is the recipient, the destination. There's the sender, who it's coming from, and this is the actual data. You'll notice that there's some frame addressing on the front of that or around that. This is the stuff on the front of the envelope. Yep, and it's the source and destination addresses. So you'll notice that there's a destination identifier here and a source identifier here. But then there's another source and destination identifier here. So is it possible to have different kinds of addresses on a network? Yes, actually. On your local network, you will have a physical address, like a MAC address, for example. When you're sending it halfway across the world, the MAC addresses are not very useful, right? So you'll use something like an IP address. Okay, they have different uses. Okay, and we'll be using both types of addresses, by the way, when we're doing networking. But you'll notice that the physical hardware address is on the outside, and then inside an envelope is the other IP address, and you'll get access to that when you actually need it. So the message size, it's possible to send the whole message at once. It's definitely possible, right? But it's generally not a very good idea. For example, if you take the letter example, if I write, I don't know, a letter that's 3,000 pages long, I had a lot to write. Will it fit in one envelope? Probably not. It's a lot of pages, so I'll need a very big envelope. That big envelope is going to get stuck in the post box, right? You understand? So the same sort of thing happens with if you have a really big message. Let's say you want to copy or send a Blu-ray disc across the internet. Let's say it's legal, right? You're not making a copy. You're just sending your own version of it. How big is a Blu-ray disc? Sorry? 40, 50, 60 gigabytes, around that sort of. Okay, that's a big chunk of data, right? Imagine if you send the whole thing in one chunk. Do you think that you can use your network for any other purpose while that transfer is happening? No, it's busy, right? So what you like to do is chop it up into smaller chunks and send those smaller chunks. Now, if you chop it up into smaller chunks, you have some problems because those chunks may or may not take the same path. The internet's pretty big. They may or may not arrive at the same time. Some of them may get lost. You may, drop some packets along the way, so they have to be reassembled as well on the other end. So in our networking model, do you think there is some part of this model that is responsible for chopping the message up and reassembling it? What do you think? Yes, there will be, and one of the layers has that as its job. Okay, so long messages must be broken into smaller pieces to travel across the network. Each piece is sent in a separate frame. Each frame has its own addressing information, and a receiving host, so on the far end, will reconstruct multiple frames into the original message. Obviously, we're simplifying a few things here, because if something's missing, you have to wait, and you might not wait forever, so you may not be able to reassemble the whole message if you don't get all the parts. And then you have to do something about that. Typically, you'll ask for another copy of some part of the message. So, in terms of the access method, hosts on a network need to know when to begin sending messages and how to respond when collisions occur. So there's a really nice example in the Netacad chapter for this. It's very simple. There are two people, and they both speak at the same time. One of them says, "What time is the movie?" and the other one says, "When are we meeting for dinner?" But they both speak at the same time. Have you ever done that on a telephone call? Yeah, what happens? The communication stops, and you both either have to back off or, start again, and one of you will be more polite than the other one, and so on, right? And you negotiate the next communication. And on the right, it indicates what happens. It says, "Sorry, I did not understand you." Same thing happens in a network. Okay, if you're trying to do two things at the same time, something's going to get garbled. And typically, the simplest example is if you're sharing, let's say, a Wi-Fi space and you're both sending a message at the same time, they will collide. Does that make sense? And then you have to resend to make sure that the collision is resolved in some way. Another thing that you need to be aware of is flow control. So source and destination hosts use flow control to negotiate correct timing to avoid overwhelming the destination and to make sure that the information is received. So, same model I used before. If I speak too fast, some words are going to get dropped. Right? Now, up to a limit. If I speak just fast enough, but not too fast, then the throughput is increased and we get a much better efficiency. If I speak very slowly, right, then yes, you'll get all the message, but we're wasting time. So there's some kind of modification we can make to the speed that will result in the best outcome. Okay. Typically, this is an issue when you have slow devices and fast devices on a network. right? If you have a slow device, you have to slow down for that device, even though the faster device could technically go faster. Another thing that happens is you have something called a response timeout. So hosts on the network have rules that specify how long to wait for responses and what action to take if a response timeout occurs. So if I'm waiting for a response, like you said you were going to send me a message and you've sent part of it and I haven't got the rest of it, I will wait a little bit of time, and then at some point I'll say I've waited long enough. I don't expect to get this message anymore. Does that make sense? Okay, and you probably have run into that. There are timeouts of different flavors for different things. All right. If you're in the labs, for example, if you don't put in on the switch the no IP domain lookup and you type in a word it doesn't understand, it will try and resolve that thing that you typed in as an IP address or an address of something, right? And it'll look it up, and it takes about a minute or two for it to just think about what you're doing, and you can't use the machine during that time. Does that make sense too? Has anyone experienced that already? Not yet? You will, right? It's something that will happen if you don't put that command in, because that's one of its purposes. Okay. Message delivery options. So this is very simple. The diagram I think is pretty clear. You have one-to-one delivery, which is unicast, one-to-many delivery, which is multicast, so this is group-based, and then broadcast is one to everyone. So this lecture, what kind of model are we using here? This is a broadcast. Okay, if I'm talking to one side of the room, we might say that is a multicast, if I'm not talking to everyone. And if I'm talking to one person individually, then it's one-to-one, or a unicast. So, for protocols, we're going to talk a little bit about the rules that govern communications, different kinds of network protocols, the roles of protocols, how messages are formatted and structured, the process by which networking devices share information about pathways with other networks, how and when error and system messages are passed between devices, setup and termination of data transfer sessions. So these are all the things that will fit into this area. Protocol interaction, we'll look at example web server and client, how those things actually progress. And you'll see on the right there in the bottom, there's a web server and there's a message going through a cloud to a PC. And you're looking at different layers. They have different names. So there's an application layer, a transport layer, an internet layer, a network access layer. And they are associated with a protocol stack, HTTP, TCP, IP, and Ethernet. So we're seeing some different protocols or some different ways of moving information or organizing information. So, protocol suites are implemented by hosts and networking devices in software, hardware, or both. The protocols are viewed in terms of layers, one on top of the other one, and with each higher level service depending on the functionality defined by the lower level services. So here is a diagram on the right, and you can see at the top there's the content layer, and the content is the question, where is the cafe? It's a question being asked by, looks like a person or someone. Then there's a conversation protocol suite, and this is the rules for this conversation to happen. First rule is use a common language. Which language are we using? English. So ideally both people in the conversation understand English. Wait your turn. So you need to wait for them to ask a question before you can answer the question. That kind of makes sense. And signal when finished. So that question mark at the end of that statement, where is the cafe, question mark, indicates this is the end of the question. Okay? And the physical layer, if you look at it, what is the physical layer? They're just talking to each other through the air in this case, right? Okay, so that's a physical example or a real world example of some of this, what's probably a pretty abstract concept actually. In network protocols, they define a common format and set of rules for exchanging messages between devices, and some common networking protocols are HTTP, TCP, IP. You will use TCP IP a lot actually in this course, so you'll see much more information about them. There's a diagram there. Now this is actually a complex diagram, so there's only one picture here. If you go to the Netacad site, you'll see that there are actually quite a few diagrams. I think there are 4 of them. And in these diagrams, what you'll see in the top one is, so this one over here, on this side, it's the person on the left is saying, I will send this message across the network using an IPv4 header. Now, he doesn't say that, but his machine says that. He wants to send a message. This guy here, this is a router, or at least a picture that represents a router. I can forward this message because I understand the IPv4 header. So if this machine did not understand whatever IPv4 is, it would not be able to do anything with it. So it does, and it can move it around the network, and eventually this guy on the right here says, I can accept this message because I understand IPv4. So we're all speaking the same language. Great. So the format or structure of the communication pieces is agreed upon. We also need to agree on the process by which networking devices share information about pathways to other networks. So at the top here, this is all those machines, those routers. Right, and the router is just a machine that allows the routing of information. We'll talk more about that in detail later. But basically, it's a network device, and they are all getting together, and they say, let us all agree that if one of our pathways is down, we will notify all connected devices. So they'll just talk to each other and say that pathway is down, don't use it. So this pathway over here has gone down, and this guy says path A is down, their neighbor says okay, okay, okay. We all know. We all agree that this has happened. So we have some processes for communicating with each other about this stuff. And on the bottom here, how and when error and system messages are passed between devices must also be agreed upon. And at this time they're saying, let's all agree that error messages will have a unique ID number so we can differentiate them. Same thing, this one is down. And so this one says error 1001, path A is down. This one says error 1002, path B is slow. It's not actually down, it's still there, but it's slower than it should be. And so we can communicate about the status of the network. And again, we're all agreeing on the standard that we're using. And the last one here is the setting up and termination of data transfer sessions. So this guy says, I would like to set up a virtual connection with you so we can exchange information. The PC over here says, I agree, we can now send and receive information between us. It is going to go through this network somehow, right? It's not a direct connection, so it has to pass through different machines, but we have agreed that this is going to happen. And so that's the common format and set of rules for exchanging those messages. There's some examples of those. So communication between a web server and a web client is an example of an interaction between several protocols. So there's HTTP, TCP, IP, Ethernet. HTTP is an application protocol that governs the way a web server and a web client interact. It defines the content and the formatting of the requests and responses that are exchanged. It does rely on other protocols to actually transmit that information, right? So IP, for example, and TCP. TCP is a transport protocol that manages the individual conversations. It divides, for example, HTTP messages into smaller pieces. We call those pieces segments, and you'll see some different naming terminology for different pieces. Because these happen at different times or different layers, we tend to refer to them with different names depending on which layer we're talking about. The segments are sent between the web server and the client. And TCP is also responsible for controlling the size and the rate at which messages are exchanged between those two, the server and the client. IP encapsulates the TCP segments into packets. You remember encapsulation? It wraps them up. So it gets the data, wraps it up, and puts its own headers and so on that. It assigns addresses and delivers to the destination host. So IP is responsible for taking the formatted segments from TCP. It assigns them the appropriate addresses, and then it's responsible for delivering to the destination host based on those addresses. Ethernet is a network access protocol. It allows communication over a data link and the physical transmission of data on the network media. We'll also see this data link layer talked about later, so that's relevant to the Ethernet here. Describes two primary functions, communication of data over a link and the physical transmission of data on the network media. Okay, we'll talk about these in more detail as we go through. So we'll look at protocol suites. There's a whole bunch, by the way, and we're not going to cover almost all of them. We'll cover just a couple of them, and that's actually quite enough because some of them are quite complex. So TCP/IP is an open standard. Other protocol suites also exist, like AppleTalk, for example. There's a bunch of different ones. You see down the bottom that diagram, the TCP/IP protocol suites. There's a lot of different things that you can that we'll talk about, I guess, in different ways through the course. At the application layer, so the programs that you might use, there might be a name system. That's the DNS. You might configure your host using DHCP, and probably you've run into that terminology somewhere. Email, you have probably used email, and there are different flavors of email like SMTP, POP, IMAP, depending on what your configuration is. File transfers, there's FTP, TFTP, web is HTTP. At the transport layer, so this is a different layer, we have UDP and TCP. We've already seen a little bit about TCP. Internet layer is IP. We have seen IP addresses. That's one of the things the IP section is looking after. We have NAT, ICMP, OSPF, EIGRP. If you continue with the Cisco or the networking courses as part of the networking major, you will run eventually into OSPF and EIGRP and so on as the routing protocols for moving information between networks, for example. We don't deal with that necessarily here, right? But it's something that you'll learn about later on. And then the network access layer, we have ARP, PPP, Ethernet, interface drivers, and so on. So in this course, what we're going to be focusing on mostly is TCP and IP. That narrows it down a little bit, but all of these protocols, you will run into them in some form, right, as we go through. So when sending data from a web server to a client, the encapsulation would be as follows. So the web server prepares the hypertext markup language HTML page. HTTP application layer protocol sends the data to the transport layer. It's going down the layers. Transport layer breaks the data into segments. Next, the IP source and destination address is added, creating an IP packet. Ethernet information is then added, creating the Ethernet frame, and that frame is then delivered to the nearest router or the nearest gateway to the next network if it needs to go outside of this network. So what I'd like to do at this point is I'm going to take you to the Netacad site, and here is just a little animation. So this is one of the nice things about the Netacad site too. They have little resources for showing specific parts, and I think this illustrates the process a little better than maybe the text does. So have a look at what happens. So the web server generates some HTML stuff. That becomes the data. That's the user data. TCP says, okay, I need to add some stuff to the front of this, the header. That's the TCP header. That's the next layer. The IP layer says, well, we need IP addresses, so we add those to the front. Now we've got an IP layer on the front. And then the Ethernet layer says, oh, well, actually, we've got to add some frame stuff around this so we can send it. When it goes down to the physical layer, it becomes ones and zeros or signals, and it gets sent down through that physical connection to the client. Okay, so the simplest way to visualize this stuff is as a series of envelopes. You get some data, and you put it in an envelope. And on the front of the envelope, you put, for the first example, TCP stuff. Then you put it in a bigger envelope, and you put IP stuff on the front of that. And then you put it in another bigger envelope, and on the front of that is the data link stuff, the Ethernet stuff in this example. What do you think has to happen on the other side? We've got to unpack all those envelopes, right, and make sure that the information gets to the right place. Typically a program on the receiving side which takes that data and does something with it. If it's a web page, it'll probably be a web browser and it displays it in a particular way. Okay, so when receiving the data link frames from the web server, the client processes and removes each protocol header in the opposite order that they were added. Remove the Ethernet header, IP header, transport layer header, and then finally the HTTP information is processed and sent to the client's web browser. And there's quite a lot of detail in here. We're just sort of glossing over it, a lot of it here, but you can see the basic process. So the next step is the opposite. So we've got a series of ones and zeros, and that series of ones and zeros is sent to the web client. Web client gets all that stuff. Ethernet header, is it for me? Okay, strip it off. IP header, again, is an IP address. Is it mine? TCP stuff, haven't really gone into much detail there yet. But once that's processed, we have the data, and the data goes to the program, and the program in this case would be a web browser if it's a HTTP document, or a HTML document in this case. Okay, so you can see both sides of it. Does this sound like a lot of work? Yes, actually networking is very stressful on the computer. There's a lot of processing that has to happen, right? Even if you're sending a single character. Okay, so there's a lot of steps. This is one of the reasons why we split the process into separate layers, because there are so many different tasks. If you have separate layers, each layer does not have to be so complicated. It can be more simple. Okay, so the next section is open standards. And so we're going to be talking about a lot of open standards. There are some, non-open standards or proprietary standards, but typically the things we're talking about, like TCP/IP, they're open standards. Those standards, if they're open, encourage interoperability, competition, and innovation. It means not one company owns the standard, so other people can use it and build on it. Standards organizations are usually vendor neutral, non-profit organizations established to develop and promote the concept of open standards. There's a bunch of these. I'm going to go through this fairly quickly. Internet standards, there's ISOC, IAB, IETF, IRTF, ICANN, IANA, right? So a bunch of different ones. You can read about the details for them here. But there's enough for us to know that there are a number of different organizations that are responsible for looking after different parts of networking in the internet in general. And so let's have a look just at IANA, the Internet Assigned Numbers Authority. It manages IP, address allocation, domain name management, and protocol identifiers for ICANN. And ICANN was the Internet Corporation for Assigned Names and Numbers. So that's the overarching group. There are a bunch of electronics and communication standard organizations. Some of these you will have heard of, maybe some of these you haven't. So IEEE, Institute of Electrical and Electronics Engineers, for example, they're responsible for things like IEEE 802.11, which is the, or 802.11, which is the wireless standard. If you've done some programming, you might have used the IEEE 754 floating point number standard, right? So they look after these things. There are the EIA, Electrical Wiring, the Telecommunications Industry Association, TIA, and so on. So there's a bunch of different communication standards organizations that you might run into in terms of the things that we use when we're working with networking equipment. We also have a an overview coming up here for the reference models that we'll talk about. Now, I've been alluding to these as we've gone through so far. I've talked a little bit about layers, and these layers will show up in these models. So there's the OSI model and the TCP/IP model. Okay, OSI model is a reference model. It provides a list of functions and it describes the interactions between the layers. We'll talk about OSI versus TCP/IP, and we will be using TCP/IP, by the way. So that's something that we'll look at later. So the benefits of using a layered model include, and I already mentioned some of these, assisting in protocol design, since protocols at each layer have defined functions. Instead of trying to do everything at once, you're basically modularizing it so that you focus on one task at a time. And that makes things a lot simpler. If you want to test it, right, you saw how many jobs there are already, right? If you try and do them all at the same time, it's going to be very difficult, if there is an error, to find out where that error is. Fostering competition because products from different vendors can work together. That's another benefit. Preventing technology changes in one layer from affecting other layers. If you change how IP addresses work, ideally that should not affect any of the other processes, unless you haven't separated those well enough. Okay. Providing a common language to describe networking functions and capabilities. And this is actually also very important for us when we're learning about it. We will talk about, for example, layer 1, layer 2, layer 3, and so on. That's worthwhile for us because we can identify and delineate what each layer does. Right, so we can specify those things. You'll see the diagram there. On the left is the OSI model. There are 7 layers: application, presentation, session, transport, network, data link, physical. In the middle is the TCP/IP protocol suite. So these are the names of the protocols that you might use. So HTTP, DNS, DHCP, FTP, TCP, UDP, and so on. And on the right is the TCP/IP model. This is the reference model for the protocol suite, actually. And so The application layer, you'll notice how big the application layer on the right is. It's 3 of the OSI model's layers on the left. Now, TCP/IP started before the OSI model was developed, right? So it's the one we're using, and so that's actually quite a lot of work for one layer to be doing, right? So that's why the OSI layer separates it into smaller chunks. Transport and network, or transport and internet layer, they seem to be fairly similar. And then data link and physical are network access down the bottom. So there is some overlap here, but it's not exactly the same. OSI reference model. So typically, you will start reading this model from one side. You'll either start from the top or you'll start from the bottom. Either way is fine, depending on where your starting point is, I guess. So starting from the top, application layer. This is where you as the user interact with the machine. You type something into your messenger and it's captured by that program, and that's the application. That application has to talk to the hardware in some sense, so it has to go through all these layers. The next layer is presentation, which provides for common representation of the data. Then the session layer provides services to the presentation layer to organize its dialogue and to manage data exchange. Transport layer is one of the things that we'll be looking at a lot more in the networking type courses. Defines the services to the segment transfer, and reassemble the data. The network layer provides services to exchange individual pieces of data over the network between identified end devices. This will typically for us show up as IP addresses. Data link provides methods for exchanging data frames between devices over a common media. So when we're in the lab, for example, and we're using these network cables to connect things together, we'll be working on a local network. We don't need IP addresses for that environment. Physical layer describes the mechanical, electrical, functional, and procedural means to transmit bits across physical connections. The actual signals that you need to generate to push them across those network cables or media. TCP/IP protocol model, created in the early 70s for internetwork communications. It's an open standard. No one owns it. It's also called the TCP/IP model or the internet model. It's basically what we use when we're talking about internet communications. We already talked about the different layers here. It has less layers than the OSI model. It's an in-practice model. It's one that's in use. And there are obviously some implications of having such a big application layer. Based on what I said before about the modularity, right? It's not particularly modularized in that sense. Also, one thing I should point out is that typically, when we're talking about the OSI reference model, we will talk about the layers. So I might say layer 2 or layer 3, right? And so on. So when we're talking about these layers, you'll see that layer 2 is the data link layer for OSI, layer 3 is the network layer. Okay, so the numbers are also important, not just the names. So in the OSI model, the network access layer and the application layer of the TCP/IP model are further divided to describe discrete functions that must occur at these layers. And so that's something that they added because, again, the application layer, it does a lot of work, and it's easier to work with it as separate chunks. So one of the things that you might find that's a little bit vague at the moment is presentation and session layer. So for example, application seems pretty straightforward. It's the program. The presentation layer might be things like, okay, you've got some data. Maybe you need to change the language or translate it in some way. Maybe you want to encrypt it or compress it in some format. The session layer is about, well, you probably use the web browser, and sometimes it says your session has timed out. Okay, so there's this idea about when the conversation is happening. Okay, so again, some of this is a little bit abstract, and we'll talk more about these as we go through, especially some other courses as well. But it helps to have a simple English representation of those for yourself. So if you can find one of those, it's helpful to sort of put those in place to see what has to happen. The next section we'll look at is data encapsulation. And actually, we'll have a break here, and we'll come back after the break. So welcome back. And we were up to the section on data encapsulation. And so this is just, again, an overview of the next few things coming up. We're talking about message segmentation, so basically breaking the communication into pieces. Multiplexing, which is interleaving those pieces. not just sending them separately. We have this idea of a protocol data unit. It's a big mouthful, but basically a protocol data unit is a data unit, and it's a general term for all the different protocols. So we'll see the exact terms for each protocol as we go through. And then we look at encapsulation and de-encapsulation processes. So large streams of data are divided into smaller, more manageable pieces to send over the network. By sending smaller pieces, many different conversations can be interleaved. You can have many conversations at the same time as opposed to just one conversation. And we call that interleaving multiplexing. And if you've done some computer architecture before, you would have seen a multiplexer, right, which takes multiple signals and turns it into one output, for example. So each piece, if you're multiplexing, must be labeled, and if part of the message fails to make it to the destination, only the missing pieces need to be transmitted as opposed to the whole message, because you're only missing some parts. So again, looking at the Netacad website, here is segmentation. So basically, the message is just being sent across. So let me just play that again. Basically, you get a message and you chop it up and you just send parts of the message across. Now, how many messages are occurring at the same time? Just the one. We can improve on that by multiplexing the messages. And so when you're multiplexing the messages, there's a yellow one and kind of an orange looking one, a yellow one and an orange one. And so there are multiple conversations happening at the same time. They're sharing the connection. Which one do you think is more efficient? The second one, right? The multiplexing version. Okay, so another thing that you'll find, though, that's part of that slide that we saw before as well, if you have a multiplexed environment, that means you need to label all the packets. And you have here a purple one and a green one, and they have their own labeling scheme. So there's a purple 1, a purple 2, a purple 3, which is different from the green 1, the green 2, the green 3. Okay? Ideally, you also have some kind of limit. It might be packet 1 of 20 for the message, so that you know if you're missing one, you're missing, say, the 20th one or the 15th one. Okay. So as application data is passed down the protocol stack, and we call it a stack because they're stacked on top of each other. Remember we saw the physical, data link, and so on. They were just layered on top of each other, so we tend to talk of it as a stack. Information is added at each level. So this is known as the encapsulation process, and you'll see this word come up frequently actually, and encapsulation was just a capsule with some stuff inside it. The form that the data takes at each layer is known as a protocol data unit. So when we're talking about generics, we're talking about a protocol data unit. So at the application layer, the PDU is a piece of data. At the transport layer, the PDU is a segment. At the network layer, the PDU is a packet. At the data link layer, the PDU is a frame. And at the physical layer, the PDU is composed of bits. So we have different terminology depending on which layer we're talking about. Now, in general, we should use protocol data unit if we're not specifying the layer. Does that make sense? Because if you use the word frame and you're not talking about the data link layer, then technically you are not referring to it by its correct name, and it's confusing for other people. Does that make sense? Okay. So the encapsulation process works from top to bottom. Data is divided into segments. TCP segment is encapsulated into the IP packet. The IP packet is encapsulated in the Ethernet frame, and so on. I showed you this example before. This was the animation before, where we just saw the different pieces. So I won't go through that animation again, but it's the same principle. This is the de-encapsulation process. So encapsulation means putting it inside the capsule or wrapping it up. De-encapsulation means unwrapping it. Okay, so that works from bottom to top. It's the process that's used by a receiving device to remove one or more of the protocol headers. And typically what they do is they get the whole thing, they look at the front of it, take off the header and go, okay, is this for me? Is this something that I need to do something with? Okay, and then if it is, they start stripping off more of the headers, and eventually they have the data and they give it to the right place. Okay, So the data is de-encapsulated as it moves up the stack towards the end user application. So basically it's stripped off the headers one by one until you have only the data left. So the next little section talks about addresses, so the network address, the source IP address, the destination IP address. IP, we've seen IP now, it's one of the protocols, right? And it's to do with the addressing. It's pretty low down the list, it's not towards the top. We have, its purpose is deliver the IP packet from the original source to the final destination, either on the same network or to a remote network. So now we've split it into two categories. Sometimes we're on a local network. That means we behave in a particular way. Sometimes we need to send stuff across another network, and we need to behave slightly differently because the addresses involved are slightly different. Data link addresses, source data link address, destination data link address, deliver the data link frame from one network interface card NIC to another on the same network. So when we talk MAC addresses, we are talking about our local network, the machines on our local network. And we have this idea of the differentiation between devices on the same network and devices on a remote network. And down the bottom there are the types of information that are added at each layer. So you can see some of the kinds of things that they add. So the upper layers, they have an encoded application data. Transport layer has destination and source process numbers. Source process numbers, or the ports, identify the program on that computer. So if you're using Instant Messenger, for example, and you're sending a message to someone else's machine somewhere else with also Instant Messenger on their machine, how does that receiving computer know that this message is an Instant Messenger program message? It doesn't, right? Unless you specify that it has to go to a particular program. And that's what you do using those port numbers. The network, destination and source, logical network addresses, data link, destination and source, physical addresses. You notice that's physical as opposed to logical. So logical addresses are your IP addresses. The physical ones are your MAC addresses. They're actually physically configured on the network cards. And then the physical layer has some timing and synchronization bits added in there. So in terms of network addresses, the network layer source and destination addresses responsible for delivering the IP packet from the original source to the final destination. Notice the word final destination. Okay, that means this message is going from me to someone else somewhere else, right? And that's why we're using an IP address. You see the diagram there. The source IP address is the IP address of the sending device. Destination IP address is the address of the final destination of the packet. You'll see there's a person sitting there at the PC on the left. They have the source address, source IP address, and on the right is a web server which has the destination or the final destination IP address. In between those machines, those routers, the circular boxes, they have their own addresses, but they're not the final destination. So let's have a quick look at this diagram. So basically here's the person on the left. Their PC is 192.168.1.110. That's the source address. Is an IP packet which goes to this router, which says, okay, you want to go somewhere else outside the network. I know roughly where that is. I don't know exactly where it is, but this guy over here knows more about that network, so I'm going to send it to them. And they will say, oh, okay, yeah, I know where that is, and I'll pass it on to the actual device on that particular network. And that might happen multiple times along, the pathway. So this is a layer 3 IP packet. Remember, layer 3 was responsible for the IP addresses. And so source IP is this, the destination IP is this, and then you have the data. So the purpose of the data link address, the MAC address, is to deliver the data link frame from one network interface to another network interface, but on the same network. That's slightly different to the diagram we just saw. Is that correct? We used an IP address. Yes? We didn't talk about MAC addresses. So as the IP packet travels from source to destination, it's encapsulated in a new data link frame when it's forwarded by each router. So in between the routers, the data link information will change. So let's have a look at this. And so here's a couple of diagrams to illustrate this. So on the top left, we have a PC. 192.168.1.110. It has a network interface card. Okay, that network interface card has an address. It's a MAC address, and this machine on this side has a network interface card which has its own MAC address. So when we are sending a message from this PC over here to this machine, we have a source IP address, destination IP address, that's this one, the final destination. But on my local network, we will be using MAC addresses. So it's the destination and the source. You notice they're green, it's these two. Can you see the ones on the other side of the router here, this box here? The other side is a different color, indicating that they are not the same MAC address. Does that make sense too? So on the other side, there's the destination address and the source address. That's these two. But the IP addresses are the same. They have not changed. And then the last diagram, we are looking at this part. So we've done this bit, we send it across here, and now we're here and we want to get it from here to here, and we need to use the blue network interface card addresses. So can you see, even if it's a little confusing, can you see that there are different addresses that you use for different purposes? One of the addresses that we need is to get it from the PC to the web server. That's the IP address. They uniquely identify those machines. As you're sending it through the network, you are using local networks, and those local networks need to have ways to get information through their own network. Does that make sense? And so some of the addresses may change as you go through the system. Okay. So the network layer addresses or IP addresses indicate the original source and final destination. Now there's a network portion, which is the leftmost part of the address, and that indicates what network you're on. And there's also a host portion, which indicates the actual machine on this network. The data link frame uses MAC addressing, and it's sent directly to the receiving device. So you have a source MAC address, which is the address of the sending device, and a destination MAC address, which is the address of the receiving device. Again, they are different kinds of addresses. So let's have a quick look at this part. So if you're communicating with a device on the same network, will you be using the IP address? You're on the same network, you can use your physical addresses. So the source address is all A's, that's this guy. The destination address is all C's. So I can just use my switch here to say I want to talk to all C's, and it'll go there. Does that make sense? You don't need to go outside of this network. Even though I have an IP address, and you'll see here like 192.168.1.110. The subnet mask for this one will be 255.255.255.0. That means that all the first 3 bytes will be considered as part of the network, and the last byte is not considered part of the network. So the first part is 192.168.1, the first 3 bytes. The last part is 110, which is the host. You'll notice for the destination, which is this FTP server, its IP address is 192.168.1.9, 192.168.1. That's a network address with the same subnet mask. Are these two networks the same? They have the same number, they are the same network. On this network, this is host 110, and the destination is host 9. So they have different numbers in terms of the machines they are on this network. So if you're sending devices to devices on a remote network, it's not so simple because you don't have that information. It's not your network. So sending to a remote network, the source and destination IP addresses represent hosts on different networks. The data link frame cannot be sent directly to the remote destination host. It has to go across multiple networks. It goes outside of your local network. Therefore, the frame is sent to the default gateway. You'll see that term quite a lot. It's basically the closest machine that will get you out of the network. Right? So it knows about other networks. Not every machine in your network will be able to do that. It's not necessary to have every machine configured that way. So you have one typically, and you talk to that one, and it knows how to go outside the network. The router removes the received layer 2 information and adds new data link information before forwarding it out of its exit interface to another network. So let's look at that diagram. So first things first, I am sending from my PC here to this guy over here. Are they on the same network? Let's have a look at our IP addresses. 192.168.1.110, assuming it's the same subnet mask. My network is 192.168.1, correct? What about the other one? 172.16.1. Are they different numbers? Yes, so they'll be different networks. So the picture illustrates that pretty clearly anyway, but just looking at the numbers you can tell that they are on different networks. So this is machine 110 on network 192.168.1, and this is machine 99 on 172.16.1. So what needs to happen is, if I want to get out of my network, I have to find the machine that's able to do that. Which machine is that? It's this machine here, which is a router. It's the default gateway, and it will update whatever the internal information is with the information needed to get it across here and eventually to the other side. Does that also make sense? Now, to find out when I get here which machine I need to get to, I need to know, well, once I'm outside of my network, which network is it going to? But which network is this device on? 172.16.1. So I need to get it out of my network. It needs to go through perhaps lots of different networks until eventually it finds a router that says, oh, I know where that is. It's one of my networks. And it will pass it on to its local network. Does that make sense? Okay, so there's actually quite a lot of work that happens there. So we've seen two different models, connecting to devices on local networks and remote networks. Okay. So in summary for this section, we looked at the rules of communication, network protocols and standards, and data transfer in the network. There's quite a lot of material here, so it's worthwhile to review particularly the Netacad site for that chapter information and have a bit of a read about some more detail on it, and try some of the activities that they have in that chapter. And that's the end of this section.